Welcome everyone to the Winds and Currents webinar. Today we have Hector Torres from JPL, who's going to talk about estimating wind work at the air-sea interface from the Spaceborne Odysea Doppler Scatterometer concept. So take it away, Hector.
Thanks, Sarah. Thanks for the invitation. So yeah, as Sarah mentioned, I will present some of the results we are getting in the context of Odysea, and particularly using the Odysea simulator that Alex put together. And actually, he has the updated version, more in a more realistic. Well, it's more realistic in terms of the error and how the instrument samples. And what else? And well, of course, there are some limitations that we cannot account in this time. But I think so far for the study that we would like, that I'm going to show is good enough. And the idea is because we have some findings that we're trying to understand, and I will at the end I would like to hear your comments about this the results. And okay, let me started. So just briefly, because I would like to show this animation because it gives us an idea of the complexity of the measurements, or the complexity of the fluid that we are trying to observe from the space. Because in particular, there are some fast evolving motions that satellite data or satellite observations may not fully resolve. So in this fast evolving actually are mostly driven by the wind stress in the atmosphere, and also, well, as you know, this wind stress forces also this high frequency, or what we call the wind driven currents in the ocean. And as you can see here in this animation, so for instance, in the top panel is the wind stress magnitude, and right away you can identify these fast propagating storm tracks. And also in the ocean you can see how these storm tracks are driven or are generating currents. So despite this discrepancies, well, the different spatial-temporal availability between these two fluids, nevertheless, there are some interactions, and those interactions we're trying to understand, and we're trying to see if Odysea is able to capture them. And so, okay, here, okay, and well, as you know, it is important to quantify the kinetic energy fluxes between the ocean and the atmosphere, because at the end, this is the way how the atmosphere forces the ocean, and depending on the scales. And now we know that at the mesoscale and downscale, we know that the ocean is also able to force the atmosphere. And so it is important to understand if Odysea is able to capture these interactions through the surface currents and the winds. So for this study, I'm going to use the new coupled simulation that Dimitri is in company with MIT folks and the Goddard Space Center are able to implement and run. Now we have 40 months that we are happy. Well, we are lucky to have it and analyze it and use it in this for Odysea. And so this is a few characteristics of this simulation. So for instance, for the ocean, we have 4 kilometers. Well, on average, we have 90 vertical levels. Also, it does include the tidal forcing, and we have hourly outputs. And on the other hand, for the atmosphere, it's about 6 kilometers. So as you can see, so the resolution is not that different between the two simulations. So I think it's a good give us a good insight about what we can do. And at the end, well, what Dimitris and the other guys did is they use an intermediate numerical grid in such a way that this numerical grid is this intermediate grid is using to passes the information from the ocean to the atmosphere and the other way around. And so this is our nature run. So at the end, I want to compare the windward estimated from Odyssey against the windward estimated using this nature run. And so for some studies have been done in the past using the Odyssey, or trying to understand the Odyssey capabilities. And the first study, it was done by Ernesto Rodriguez. Well, he derived the theoretical and the theoretical background in terms of the relationship between the radar parameters and the surface current random error. In the same year, Doodle Shelton, he analyzed the capabilities of Odyssey, assuming a constant error, and he tried to understand. Well, he focused on the spatial derivatives, relative vorticity, and divergence, and see how the error impact the velocity gradients. And a few years later, well, 1 year later, Alex Weintier developed the Odysea simulator. So in 2019, well, Alex, he published this paper, and this is the first paper when in a more realistic way, Alex Weintier identified the future capabilities, also how the random error impact the velocity gradients, and how the sampling depends on how the surface current error it depends on the wind speed, as you can see here in the right panel. So here is an example of the study that Alex did, and I put this figure here because it emphasizes how the random error depends on the wind speed. For instance, in the top panel, you have this very noisy velocity current, surface current speed, and on the wind speed about 3 meters per second, and as the wind speed increases, so now you're getting a more clean surface current, and as soon as the wind speed increases about 10 meters per second, so now you have the surface current random error decreases of about 10 centimeters per second in such a way that, I mean, it's so clean. So in this study, so I'm trying to move forward, and now trying to understand how Odyssey or future capabilities of Odyssey are to further assess the future capabilities of Odyssey in the context of the surface current, of the kinetic energy fluxes between the ocean and the atmosphere. And so let me just move forward. And so here's some capabilities that the present Odyssey simulator takes into account. For instance, the spatial resolution is about 5 kilometers. The temporal resolution is twice a day at mid latitudes, and the wide swath is about 1,700 kilometers, and the baseline error is about 35 centimeters per second. No, sorry, here is 0.35 meters per second for surface currents, and 1 meters per second for the ocean winds. And as I mentioned before, this simulator takes into account the surface current dependence on the wind speed, but also how the surface current random error varies across the swath. So this is here emphasizing this slide. So two types of error are considered in the simulator. One is the azimuth diversity, and the other type of error is the surface current random error that depends on the wind speed. So for instance, here in the right panel, you can see how the random error is distributed across the swath, and because of the poor the poor azimuth diversity at the center and at the edges, so the error increases a lot. And so the other type of error is associated to the wind speed. So for instance, if the wind speed is about 4 meters per second, so you can have a random error of about 30 centimeters per second at the center of the swath, and then increases huge. but as soon the wind speed increases, so then the random error decreases of about 15 centimeters per second when the wind speed is 12 meters per second. So here, so in Alex's paper, he further described this dependency, and so you want to have more insights about it, you can go there and take a look. So this is the type of error that the simulator are considering. And now looking at now this error, how they are distributed in geographical space in latitude, longitude. So for instance, here is an example of the Odysea SWOT. And the top panel is the surface wind magnitude, and the bottom is the surface current standard deviation of the error. And as you can see, if the wind is the magnitude of the wind is weak, is quite low, about between 3 and 5 meters per second, the standard deviation of the error increases a lot. And for instance, in the Southern Ocean, well, in this example, I'm just showing a wind speed of between 10 and 15 meters per second. The wind speed, the random error decreases quite considerable. And just to further emphasize this, the dependency. So here I'm plotting the scatter plot between the wind speed and the surface current standard deviation. So you can see here how the standard deviation of the error decreases as a function of the wind speed. So here in the analysis or the result that I'm going to show, I use 5 meters per second as a threshold. So all those data were associated to low wind speed, or when the wind speed is below 5 meters per second are avoided. So I'm not considering, because the error is quite large. And so here is at the end, well, kind of the process that I follow to make the Odysea like data. So I use the model error that the Odysea simulator takes into account. And so one of the process is that the steps that I follow is I skip the center, because again the error increases a lot. So we have an nadir gap of about 100 meters, 100 kilometers, and also I just skip the edges of the SWOT, the left and right. So at the end, so from the sorry, here is 1,000 kilometers SWOT. So at the end, I'm skipping 100 kilometers at the center and 50 kilometers at the edges. So I avoiding 200 kilometers of data because of the error. So this is how it looks like. So here you have the nadir gap at the center, and also here I blanket blanket those areas when the wind speed is below 5 meters per second. So that's why you can see here these patches here without data. And at the end, combining the error model plus the sampling, I get the what I call it Odysea plus error. So you can see this how the Odysea SWOT looks like at 5 kilometers resolution without any spatial smoothing. So just considering, so just for you to give an idea how the Odysea will eventually observe. And so this is the global coverage. So this is just one day of data. So in one day you can have about 90% of the global ocean covered. And the top panel is the surface currents, the middle panel is the wind stress, and the bottom panel is the windward. So something that I would like to emphasize is that, for instance, in the top panel, which is the surface currents, there is a smooth transition between SWOTs. So you can see, so by eye, there is not this kind of jumps between, or discontinuities between in the current because of the sampling. On the other hand, in the wind stress, because of this fast evolving motion, so sometimes you can see some jumps or some discontinuities between SWOTs. You can see my pointer. So for instance, you look at this structure here, you can see some kind of discontinuity between consecutive SWOTs. And at the end, of course, when you compute the windward, so you will have this discontinuity is associated to the fast evolving motion. So now the idea is, okay, considering the error model, considering the sampling, so how well is Odysea does to diagnose the windward. So here is an example. So I compute the windward average over 3 months in 2 seasons. One is in January, February, March, is the top panels, and the other season is July, August, September. This is the bottom panel. The left panel is the couple simulation, so or the nature run, and the right column is the Odysea plus errors. So positive means that there is an injection of kinetic energy from the atmosphere into the ocean, and negative is in the other way around. So by eye, there's no other big differences between the nature run and Odysea plus errors, and both of them capture the geographical distribution of the windward. Higher injection of kinetic energy in the northern hemisphere during the winter season, and high injection of kinetic energy from the atmosphere into the ocean in July, August, September, which is the winter season in the southern hemisphere. So, and also, well, you can see these kind of lines here. Those ones are associated to hurricanes in the tropical bands. So even though this kind of feature evolve, propagate quite fast, even though Odysea is able to kind of capture them. Not of course not entirely, but at some, but partially well resolved. So by eye there is no big differences. So however, if I plot the differences between the nature run and Odysea plus error, now you can see the distribution of the differences and how big they are. In January, February, March, the left panel. So the error, the differences is quite small. It's between 0 and minus 25 milliwatts per meter square. On the other hand, what is a little bit striking is in July, August, September. So you can see here there is kind of a systematic underestimation of the windward along all the northern hemisphere between 30 degrees north and 70 degrees north. And so this is something that we are trying to understand what is causing this underestimation of the windward, whether this error comes from the instrument error, or is because of the sampling, or what kind of error produces this discrepancy. And so my first question is, okay, whether the windward is sensitive to the uncorrelated random error. So I did my first analysis. And here I consider two scenarios: the baseline requirements, and another scenario where the random error is for the surface current is about 1 meters per second, and just to see if the windward changes because of the random error. So as you can see, the two lines, the blue and the orange line, matches quite well, and so it means that the windward is insensitive to the uncorrelated noise. Something also that you can note, you can identify is the how small is the differences in January, February, March. On the other hand, in July, August, September, so some areas, in particular here in the northern hemisphere, the differences can be of about 10 milliwatts per meter square. So this is something that I would like to try to understand. So here, this spike here, this associated to this here in this close to England. I guess this is because we are not fully resolved close to the coast, or something, or maybe in interpolation processes, or maybe. So this is right at the coast. But what I'm interested in is what happened in the ocean interior. In this large discrepancy here and at mid latitudes in July, August, September is associated to this systematic underestimation of the windward in Odysea. So to further emphasize, okay, First, I wanted to know if this discrepancy is associated to the measurement errors. So here I'm showing the windward estimated using Odysea without the model error in blue, and the orange line is Odysea plus error. So here I'm considering the model error, and in green is the nature run, is the coupled simulation. So again, in January, February, March, there is not much problem. There's a good consistency. And we know that in this season, we have a strong winds in the northern hemisphere. On the other hand, in July, August, September, at the same latitudes. So now there is a difference of about 50% between the nature run in green and in Odyssey, even without the errors. So this means that the discrepancy between the nature run and Odyssey does not come from the instrument error. So this is something else. So now the question is, okay, what type of error explains the difference in this latitude in this season? So are we missing a geophysical signal? So because of the sampling, we are not fully captured some fast evolving motions. So how to explain this difference? So my first hypothesis is the wind speed anomalies. So here I'm showing the wind speed anomalies in June, January, February, March, and July, August, September. Again, in January, February, March, we know that the wind speed can be quite large because of the storm tracks in this season. And on the other hand, in July, August, September, so there is kind of we reach the minimum wind speed amplitude. So here we have between 5 and 10 meters per second. So I wonder if the weak wind speed causes this discrepancy, because again, the post-processing I'm using is I'm eliminating those data where the wind speed is smaller than 5 meters per second. So this is something that this is one hypothesis. The other hypothesis associated to the fast evolving motions, again, because we are sampling twice a day at mid latitudes, but we know that there are some high frequency motions that we cannot fully capture. So this is if so this associated to the sampling, not due to the instrument error. And so this is two hypotheses that I'm trying to figure out. So this is kind of the question that I would like to mention to you. You have some feedbacks and how to proceed. Again, this is an ongoing work. So here's just a briefly summary. Odyssey works quite well if the wind speed is larger than 5 meters per second. The windward is insensitive to the uncorrelated noise, as I showed it. If I increase the surface current error of about 1 meters per second, there is not much differences compared with the baseline requirements. And however, the question that we're trying to understand is what causes the discrepancy of about 50% between the nature run and Odyssey in July, August, September. So we have these two hypotheses that we're trying to test. So I will happy to hear your insights. And so that's it. That's for today. You have some questions, comments? I will happy to hear you.
Thank you so much, Hector. This is great. We do have space for questions, and I'll let people start thinking about questions. If I can start with a really basic question. You talked about the model run you're using for the coupled model. And I'm sure people want to know how they can get access to it. You mentioned it's available.
It is available. So far, it's just by sending an email to Dimitris or send an email to me. And there is there's only 4 months available. This 4 months is part of the spin-up period. Now we have 40 months, but that's a per request. You can send an email to Dimitris or send an email to me, and we're happy to coordinate to share the data.
So,
Thanks.
so to add to that, anyone who has a NASA account can access all of it. And we've tried to put parts of it in many places to make it as accessible as possible. There's no restriction in using it. It's just a difficulty of transferring it. So yeah, send me an email. I'll tell you all the different ways where the model is available and accessible.
Thanks, Dimitris. And in the chat, Tony asked 14 months total integration.
Yes, so 14 months total integration, so 4 months of a spin-up. And yeah, so 10 months of without spin-up.
Great.
Yeah,
okay.
14 months total. We're not going to continue this. We're working on the next gen, putting our effort in getting one that's twice, have half the grid spacing and more vertical levels, both in ocean and atmosphere. So, but in terms of this one, that it's going to stay 18 months, yes.
Okay. Thank you. Fabrice had his hand up and I don't know, and then he took it down. And Schwanting Gao has his hand up. So why don't we let Schwanting go first and we'll come back to Fabrice.
Yeah, sure. Well, great talk. I have a question about the calculation wind work. So I might have missed that. So do you have like a definition for that?
Oh, yes. Well, is it here? I'm considering the total, well, what I call it total wind work. Is the dot product between the wind stress and the surface current. So here I did not use any spatial filter or temporal filter. I just considered all the components, either the high frequency or low frequency components in both in the wind stress and in the currents. But yeah, this is just the dot product between the wind stress and the surface current, then to have these results after the dot product. I averaged over 3 months to get this seasonal variation.
I see. Another quick question is about the area at low wind speed. Do you think it has anything to do with the capillary wave or maybe the gravity wave range?
It can be internal gravity waves because we not fully resolve them. It can be also near inertial waves. And it can also be, yeah, mostly that in near inertial waves in the ocean, internal gravity waves, and also, well, in the atmosphere, we also have these fast propagating atmospheric patterns that we not fully resolve twice a day. So yeah, it can be this. If we are missing some geophysical signals, it can be those.
I see. Well, thanks.
Yep.
Okay, well, there are a lot of hands up. Let's go to Fabrice.
Hi, Chris. It was great talk and very nice to see this thing come alive and try to figure out what we will be observing the satellite. So it's really nice. This stuff is being done and pursued from what Alex was doing before. So that's really great. Of course, you're looking at some highly integrated estimate of something which then you perturb with random errors, or the random errors in the end are dwarfed by the averaging. So I think that's very good for us for the proposal to show that we're looking at something which is very robust. At the same time, I was wondering if this fully integrated wind work is really the most important thing we want to look at, or maybe we want to also break it down with different components, the near-inertial part and the other parts, and so at that point, I guess the random errors maybe become a bit larger. But yeah.
Well, I can show you. I did a further analysis, just focus on the mesoscale wind work. As you say, this that I decompose. Right. Now I decompose in the total wind work into high frequency and low frequency component, and from the low frequency component, I just split it into large scale and mesoscale. If you have the time, I can show you. You are interested. And as you know, what you can imagine, the error decreases. Let me stop sharing and share something else here. give me a second.
So what you're looking for, that I guess the only reason why you get a difference in your estimate at the end, you were wondering, but I guess it just it's only the sampling, right? So depending how you do the averaging in time, and whether you
Exactly, yeah.
fit in for
Okay,
the
let me
low winds
share.
or
Oh, wait, can you see a PDF?
Yep.
Yes.
Some global maps. Okay, here, okay, let me have the equation here. Okay, here. Okay, now what I did is I decomposed the total windward into something like call it time mean component and time dependent component. And in the time dependent component, I split it into high frequency, which takes into account near inertial waves and fast propagated atmospheric storm tracks. And these two terms are for the low frequency component relative to 3 days. And the middle panel is for the large scale component, and the third panel is for the mesoscale component, or the so-called eddy killing effect. And it's showing here. So the top panel is the nature run. Now, and the middle panel is the Odysea plus errors. And the bottom panel is the differences between the first two panels. Now, first to notice is that the amplitude of the windward now decreases about a bit down to 2.5 milliwatts per meter square, but also the errors. Now the errors, the differences between the nature run and Odysea plus errors is smaller than 0.5 milliwatts per meter square. So you know, because now at this time around, I remove all the NIO component, the fast evolving propagated atmospheric patterns that we cannot fully resolve every twice a day. Now the low frequency component is more I think is we fully resolve twice a day, and because you can see the error, how the error decreases significantly from 10 milliwatts per meter square down to about 0.01 milliwatt per meter square. So this is something. Well, this is this included the eddy killing effect. So I don't know. This is one of the right quantities or components to look at it, but yeah, at least we know that the eddy killing effect, we can resolve it. Well, here more accurate than the total windward. But yeah, so this is something also I computed it. So and now with Mark Bourassa, he gave me some insights. So now Mark Bourassa is interested in just not considering the total surface current, but just consider those currents when the magnitude is above 20 centimeters per second. So this is something also that I'm working at the present time. But yeah, I think this also. I mean, this is also related to your question. If there's another quantity of the windward, not considering the total windward.
Thank you very much.
Yeah.
Thanks. Should we go to Mame Hell?
Sure. Thanks. As mainly just a clarification question, is your error in direction or only in amplitude?
It's the amplitude.
I see. So
yeah, this one. Yeah, well, this error.
The error you add to the Odysea emulation, it's only you just change the amplitude, not the direction of the vector.
You do.
You do, because you changed the amplitude.
Yeah,
I see. Okay, but then, so this error that you see there in summer, you add that, and you add the error to the Odysea stuff after you removed everything below 5 meters per second. So you first remove low winds, and then you add the error.
Exactly. Yeah, like here.
So then you get a random direction, like a larger random direction there, and that since you do the dot product in the windward, you have like it's a weird filter that you create.
Which one? The 5 meters.
Well, it's all right. You have a vector that is 5 meters per second, and you add an error that is random on that, and then you multiply that with another vector.
Yeah.
So that might be an explanation why you get this large error.
Oh, okay. I see. So you're saying it's so
Maybe the
so
error.
you're saying it's not the sampling. So this difference is not due to the sampling because well
I don't know, but so if you had low amplitudes and you add a random component to it and then multiply it with an ocean vector that's also kind of random, then you sit in more in the noise. So the order of the procedure might matter a lot.
well yeah, well here for instance here in this plot the blue line is Odyssey, but not considering the error field. And the orange line is when I added the random error. And as you can see, in both cases is the same, is about the same. So that's why that's why I'm saying that this discrepancy is not due to the error. And I think for my hypothesis most due to the sampling, because we are not fully resolved fast evolving motions. So that's my hypothesis.
Yeah, probably I'm my suggestion is not correct then. Thanks.
Yep.
Thanks. Let's go to Mark Barassa.
Nice talk, Hector. Can you put your the spatial and temporal scales of your mesoscale wind work in the context of say classic altimetry and SWAT capability?
Oh yeah. For instance, here, the plot that I show. Let me going back. Share my PDF. So here now, my definition of mesoscale windward, I consider, I apply a spatial filter with a cutoff wavelength of 250 kilometers and a temporal running average of three days. So here is for those scales, for those temporal scales larger than 3 days, and spatial scales between 250 kilometers down to the 5 kilometer resolution. And I did a further analysis in trying to mimic how Aviso and QuickScat observe and then compute the wind work. So this is a figure here in figure 8. So here I produce synthetic data set to mimic Aviso. This is Aviso, which I apply a 7-day running average, and QuickScat using a 12 hours sampling and a spatial resolution of 50 kilometers for the wind stress. And the purple line is and also for Aviso I apply a smoothing of 130 kilometers, and the purple line is the same, assuming the same smoothing, spatial smoothing of 130 kilometers, but now considering observations every day. And for the wind stress, I keep the same spatial and temporal resolution. Now, as you can see, the red line, I mean, underestimate the windward. Now, if I increase the temporal sampling, the purple line, now I'm getting a better estimation of the windward. However, it's not like Odyssey, as you can see here in this blue and orange lines. So this is for January, February, March, and this is for July, August, September. Now the underestimation is more emphasizes in July, August, September. Even for the purple line, when considering one day sampling, Odyssey does a better job. However, it's not sufficient, in particular in the northern hemisphere again. So that's why I'm trying to understand what is causing this discrepancy. But yeah, this is kind of I think answer your question, Mark. If I produce the synthetic data sets.
Yeah, thank you. That answers that. That northern hemisphere might have a lot to do with the transitory nature of the storms, whereas in the southern hemisphere you get more persistent high winds in a lot of areas.
Persistent.
All right, thank you.
Thanks, Mark.
Thanks. There are a couple questions in the chat. Shikar, do you want to unmute and ask your question, or should I read it? I'll go ahead and read. He says, very interesting work on the error on June, July, August. Is it from high frequency, low wave number? Maybe you were just addressing this, but
Oh, yeah, there's very interesting. Is it on the high frequency? It is indeed now. Okay. I think, go back to my PDF. I think that explains more. Addresses that question. Wait, give me a second. Okay, this one here. Let me share. Okay, can you see my PDF? Oh.
yes.
Okay, yeah. To answer the question, the question in the chat. Okay, Odyssey with the twice a day observations at mid latitudes. So we are resolving this part here below my black line. So here what I'm showing is the frequency web number spectrum of surface kinetic energy in the ocean, the wind stress, and the windward. So I think what we are missing, in particular in July, August, September, even if the windward is quite small, we are missing the NIO and the one associated to these beams. I think these beams are associated to the transient event that Mark Bourassa mentioned. So on the other hand, in January, February, March, we know that the inertial waves are very energetic, and also the transient events are also energetic. But even though we are I mean, the discrepancy between the nature run and Odyssey is not that large as in July, August, September. So I'm wondering, yeah, I mean, how to explain, because I think this also emphasized so what we are missing with Odyssey, but why in January, February, March we are fully resolved. Well, we are getting better than in July, August, September. That's so yeah, the discrepancy I mean, from my understanding, that it concerns the high frequency and low web number. But why in January, February, March we know that the NIU are more energetic and the transient depend are also more energetic, we are doing a better job. And so yeah, that's why that the question remains. But for me, I don't fully answer it yet.
Yeah, that's really puzzling. So I guess what I've been wondering is, one of the sampling issues is about on a sun-synchronous satellite, you're sampling at the Nyquist frequency of the diurnal cycle, and so you might expect that in places where you had a really strong diurnal wind or diurnal current effect, as Megan was talking about last week, in relation to temperature, that there might be some interesting aliasing effects. And so it's striking that you don't see big issues in the tropics where there are strong diurnal winds. But I'm wondering if it might be helpful to tease apart what's happening in the tropics or in places with a strong diurnal wind as a sample of what could be happening with the sampling issues at high latitudes, where it's less locked to the diurnal frequency and maybe harder to tease apart.
Yes, that's yeah.
So, but it looks like you're, except for the fact that wind work is a lot less in the tropics, it also looks like it's pretty good.
Yeah, that's a good job here. I guess because the scales are quite, I mean, the temporal scales are longer than those ones at mid latitudes. And also the Southern Ocean, it does a good job. I think that's Mark Bourassa mentioned, that you have a persistent winds in one direction. On the other hand, yes, maybe here. Yeah, I don't know. I don't know what happened here. I don't want to speculate too much.
It's a good problem. So in the chat, Fabrice has put an announcement about trying to set up a potential working group of some sort to look at correlated error between currents and winds, and through wave effects and in the GMF. So Fabrice, do you want to say anything more about that? People should contact you if they're interested.
Yeah, nothing more. Just So right now with uncorrelated errors, things average out really nicely. Hopefully, the uncorrelated errors won't be so big, but so yeah, I don't want to raise any red flags at this stage. We just want to, it's more like a process study, see what's going on.
Sounds good. I guess I had one additional question, and people can think if they have any others, but I wondered about precipitation effects and what happens when, for example, high winds correspond to precipitation.
Well, I think that question can be, maybe Alex have more insights about it. Alex, are you there? Ernesto?
Yeah. Hey, sorry, I was just a meeting. Yeah. Well, in places where there's precipitation, Odysea generally doesn't work so well. So I think, yeah, we probably just lose those places, and there would be some amount of bias due to that. However, there are good things about Odysea. Mostly due to the footprint of our antenna. It's small enough to where a lot of thin rain bands, we can kind of see around them much better than legacy scatterometers could.
So does the analysis you've done, Hector, include precipitation as a blanking process?
No, not yet.
Not yet.
Not yet. Yeah.
So that'll be an additional adventure, I guess.
Yes, addition.
And Mark says for mid-latitude storms, there's a large area of rain-free high winds behind cold fronts. So lots of stuff that we can certainly hope to measure.
Behind, yeah. Okay.
So, well, are there any other questions? If not, this has been really wonderful, great discussion and really wonderful presentation. So thank you, Hector. I'm going to stop the recording.
Yep. Thanks, Sarah.
And
Thanks, everyone in the audience.